There we go. So you probably recognize this scene in which Indiana Jones wants to steal an idol. And in order to avoid triggering the security mechanisms in this cave, he has this bag of sand that he tries to replace the idol with without the system noticing. And so we're trying to do sort of the same thing, except there's no rolling boulder coming after us, luckily. But we want to replace an instance of our application with a new one without it being noticeable at all. And this talk came to me when I was working with a platform, I think it was my first Kubernetes platform, where we had applications deployed. Yeah, so background. We had applications deployed in Kubernetes, and we had set up alert or uptime alerts for these. And we noticed that during deployment of new versions of the applications, sometimes, not always, but sometimes we would get errors. And I couldn't really understand why, because this is something that, like, it's the main point of Kubernetes when you're new to this. Kubernetes is sort of like the tool to do just continuous deployment of your application and everything sort of taken care of. And they have a lot of tools for this and some important principles that it uses, which are you have multiple replicas of your application. And when you do a deployment of a new version, you introduce one by one, or you introduce a new set of replicas for the new version, and then you kill the old ones so that you ensure that you always have some running versions of the application at all times. And Kubernetes achieves this by using something they call a probe. And it has three, or it achieves this, how it knows that, that an application is alive and that is ready. And it achieves this through the probes. And we have the liveness probe, which is used to figure out if the pod is healthy, so to speak, that it shouldn't be killed, basically. And we have the readiness probe, which determines whether or not the pod is ready to receive traffic from the outside. And then we have the startup probe. And this is something that was introduced a bit later to support applications that might take a long time to start the first time. For example, loading a lot of things into RAM or other things that you want to take into account, or you want to sort of have the lenience for that when you start the application, but it's not something you want to be able to accommodate during the lifetime of the application. And it's important to note the difference between these, especially liveness and readiness is something that I often see are configured identical for your application because you don't really know the difference. Like, okay, I want some probes. I just copy readiness to liveness or vice versa. But the thing is, as I said, the liveness probe is the one where you want Kubernetes to restart the application if it has failed, if it's deadlocked, if there's something completely wrong, but not otherwise. And the readiness probe is one where you want it to fail as quickly as possible as soon as you think there might be a problem with the requests coming to that probe, no, to that instance or pod. Sorry. So an example of a liveness probe could be this, where you have just a reasonable delay for starting. You have a period of 5 seconds between each probe. You have a timeout. I think it's default 3 seconds. I think that's a good default. And you have pretty high failure threshold. So you want several probes to fail because you don't want, if you have a failure threshold of 1, then some network trouble would just kill the pod, right? You don't want that. But then when you get to the readiness probe, you want a low failure threshold. Because here it's better to be safe than sorry, because you already have several replicas. So if there is a problem, or if there might be a problem with the pod, you want to sort of take it out of the pool until it responds to the readiness probe again, because it will still be probed, it's just that it won't get traffic. And then for the startup probe, it's similar to the liveness probe in that if it fails, it will restart the container or the pod. And here you will have a very high failure threshold. You can have a long period and lower threshold, but those two combined, 10 times 30, means that it will take 300 seconds until the starter probe fails, and at which point the pod will be restarted. Then we have something called a deployment strategy. For a deployment, this is by default rolling update, so it's not something you really need to configure, but you also have the options to define max surge and max unavailable. And these are configurations that you can use to define how many instances of the new version you add when you do a rolling update, and how many sort of you can take down. So let's say you have 5 replicas of your application, then you have max surge of 3 and max unavailable 2. So when you do a new release, what happens is that 3 new instances are added immediately and 2 are taken down. So well, I don't know, I don't remember. Yeah, I said max unavailable 2, yes. So 2 are taken down, so that's 5 minus 2 equals 3 left. And then whenever one of the new ones respawn ready, you have the sort of allowance to take down a new one, and then this continues until you have only 5 new versions. Then we have something similar called a pod disruption budget. And this is used for not releases or rolling updates. It's used when you reschedule a pod, because there are 2 reasons why a pod might be taken down in Kubernetes. And one is if you update the deployment. Another is if Kubernetes, for some reason, for example, if you drain a node for upgrading the cluster, or if there's some other prioritization happening, that means the Kubernetes will kill a pod or move a pod from one node to another, then it can kill them. And this resource here specifies that even though Kubernetes is allowed to do this, it should ensure that you have at least 2 available replicas at some point in some place in the cluster. So these are a lot of tools for achieving uptime and resilience in this area. So it should be sufficient, but it's not. And why is that? So before I started digging into this, I thought maybe this is something that's solved by some tool. I was pretty new to Kubernetes at the time, so I was thinking this should be a solved problem, right? This is something that everyone has encountered, and then it's just fixed by someone. So I tried a Argo rollouts deployment tool, and I still got 500s. So it didn't help. But what I did realize or notice when I did this is that the 500 errors didn't come when a new pod entered the pool. They came when an old one left. So this was a very good starting point for digging into how things work in Kubernetes. And here's also where it gets a little bit complicated. And if you have questions, I have my phone here. I'm going to try to keep track. If you ping me on Slack, I'll see if I can accommodate the question, and also if I notice it, but I think I will. So feel free to just fire a question during the presentation if there's anything unclear, because if you fall off at some point, it's going to be hard to follow along, I think, if you don't clear that up. But let's get into it. So first I want to start by just presenting a few terms and concepts of Kubernetes, which might be known to a lot of you, but they're important to understand to follow. So a pod is a Kubernetes resource, a configuration object that's used by Kubernetes to reason about containers. It's the smallest sort of entity around the deployment area of Kubernetes, and they contain metadata about a pod. Or about the pod, of course, but about containers. So which containers you want to be running in the pod, and environment variables for those, and other, like which images, which tags. You specify which volumes you want to attach to the containers, and you also specify some other metadata on how Kubernetes should relate to that pod. You use tags and annotations and labels, etc., to sort of be able to reason about it. And then you have something called endpoint slices. And this is another configuration object which is a collection of IP addresses used for routing traffic. So this is also stored in by the API server as something you can sort of hold and reason about and retrieve. And then you have the API server, which I mentioned a couple of times now. And this is the heart and brain of Kubernetes. Everything happening in a Kubernetes cluster goes through the API server by someone updating or creating a configuration object, sending it to the API server by doing that, and then that is then propagated to other interested parties. We call them controllers usually. And this sounds a bit abstract, the API server, you send things here and there, but it's literally an HTTP server where you have an endpoint, an API endpoint, and you post things to it, or you get things from it. And the controllers, they subscribe to objects by establishing a long living connection with this URL, for example, and this will enable them to have this connection open and then just get new items as they are created or as they are updated. Okay, so that's some basic theory, so let's investigate a bit. We mentioned that it happened during the termination of a pod. So first, let's go through the creation process of a pod. And now I'm going to use my cursor so you can follow, because this is a bit of a mouthful of a diagram. But this is what happens during a pod creation. So here we have me or someone saying 1 pod, please. For example, using kubectl run, sending that to the API server. The API server then just verifies that I have access to do this, and then it stores it. And then that newly stored object is picked up by some component of Kubernetes called the kube scheduler, who notices that this is a pod that hasn't been scheduled to a node being a virtual machine or something that runs like a component of Kubernetes. So it decides where to run it, stores this back to the API server. That then is picked up by the kubelet of the node in question, who sees that this isn't pod that should be running here. I need to do that. And so it fires off instructions to the container runtime, which starts the containers needed, to the network interface, who sets up networks and attaches IP addresses, and the storage interface who mounts the volumes. And when all of these are done, the IP address of the pod is then stored back into the object, and the kubelet starts probing the ready endpoint, if it exists. And then when that either succeeds or right away if it doesn't succeed, the status of the pod is set to ready and stored back into the API server. And then the ready pod is picked up by the endpoints controller, who updates the slice with this IP based on these labels that I talked about. So the point is that, and then that is picked up again by the kube proxy who updates the actual routing. So the point is that the network update, the routing update happens. It literally can't fail in this section because it needs to be ready to actually do the routing update. But then when we get to the termination process, it's a bit different. And here you can see time is on the x-axis, and this is sort of a diagram. I don't think things take a longer time because there are more letters in them though, but like in principle, this is what happens. So the API server gets the delete pod instruction, stores that on the object, and that is sent to the endpoints controller and the kubelet. And now it becomes a race against time, who can finish its job first. And as you can see, for the endpoints controller, there is a lot of back and forth. It needs to be removed from the endpoint, that is sent back to the API server, that is then sent to the kube proxy, who does the actual removing of the routing. Whereas the kubelet receives the instruction or receives the updated object and just fires. So here you can see you have a small window of 502, but in reality, it's much more like this, because the application usually stops serving new requests immediately when it gets the signal to shut down. Because Graceful shutdown, as I'm going to come back to, it's mostly about finishing what you have started. So the window is more like this. Now, my first instinct was, this is something that I can just sort of fix in the ingress controller, because the ingress controller is between you as a user and the service. So every request coming in from the outside goes through the ingress controller, like a web server, and then that again probes or communicates with your application. So it should be able to, or it is able to, pick up on that failing communication. And that should be transparent to the user, because then it can just retry or can try to fire off to a different pod. And I tried several nights in a row to get this to work, but I still got errors, 504s for some reason. Anyway, I didn't really dig into it that much, because I realized that even if I got it to work, it would be a bad experience for the user, because the request would just hang while the controller tried again. And this shouldn't be necessary, because we know that there are available replicas that are ready to serve us. So we should find a better solution. Let's dig a bit into this sig term signal here. We know that the kubelet is shutting down the pod, and how does it do that? So again, for more diagrams, the API server has a new object where a pod is marked for termination. This is sent to the kubelet. And now we start the termination process. Here, the first thing that happens is that the kubelet checks if there is a pre-stop hook defined for the container. And if there is, it executes that. And then afterwards, it figures out how long did that pre-stop hook take. And then it subtracts that time from the termination grace period, which is 30 seconds by default. And it sends a request to the container runtime. Hey, stop this container. You have, say, pre-stop took 7 seconds. So then kubelet calculates that stop this container, you have 23 seconds. And then the container runtime sends a sig term, waits 23 seconds, and if it still is alive, it sends a sig kill. It kills the application. So let's go through each one of these. The pre-stop hook is something that you define in the configuration of the deployment, or the pod, actually. And it's something that you can define per container in the pod. And it's an action that you perform before stopping the container. It can either be an exec, just run a script or run a command. It could be an HTTP request, for example, if you want to call webhook for some statistics or whatever. Or there is a sleep action pretty recently made available, and I'm going to come back to that. Then we have the graceful shutdown period, which is not, I couldn't really find an explicit definition of this, but it's something that I've heard of for years, and we have this general notion that this is where you finish what you've started, but don't take on any new work. You just want to sort of finish in-flight requests, usually for web services. And then we have the sig kill, which is executed or sent by the CRI or container runtime after the grace period is completed, and sent to all processes in the container. Okay, so if this gets too technical, I'm now going to dive even deeper, and I'm going to tell you when I come back up. So you're allowed to just phase out for a little bit here if you want. So what are signals? Sig term, sig kill. These are software interrupts sent by the Linux kernel to applications used for very light type of inter-process communication. And there are mainly different reasons and ways to kill a process. And the behavior that I'm going to list up is by convention, and almost all signals can be overridden if you have a signal handler. Sig kill is the only one of the more common ones that I could see, which you can't trap, you can't catch it. It will always be triggering a termination where the kernel just does that. So sig int is what's sent if you do Control-C on your computer. Interrupt, sig interrupt. Sig quit is usually a very very hard type of signal where it's equivalent to sig kill, except that it also does a core dump, so you can debug. But for example, Nginx uses it to gracefully shut down. So Nginx also uses sig hup or sig hangup to do a configuration reload, where it finishes all in-flight requests and reloads the configuration and then does a sort of a soft reboot. And then we have sig term, which is conventionally the one you send to gracefully shut down, like, hey, you should stop. But it's a bit of a special case in Kubernetes because we use containers, and containers have process namespaces, which means that they have their own little world inside the Linux environment. So each container has a PID1, process of ID 1, which is usually the process that is set as the entry point or command to the container. And then sig term by the container runtime is sent to that particular ID, that PID. But PID is special. PID1 is special because PID1 is in a regular Linux system reserved for the init system, which is used to sort of govern the whole machine, basically. So it's expected to have explicit handlers for signals. And if a signal is sent to PID1 and it's not handled, the kernel won't do anything. And I'm going to show you in a diagram here. So here on the left side, we have the situation where the kernel in the blue and some application in purple with PID15, just a regular application. The kernel sends the sig term signal to the application, and then that signal is pending on the application. The application doesn't have a signal handler, so it just stays there. And then when the kernel checks again, it's still pending. And the kernel's like, okay, shut down, terminate, sig kill, or the equivalent. There's no signal there, but it kills it, basically. And then you have the same situation, except the application has a signal handler. So when the signal is sent to the application, it's picked up by the signal handler, and then it can initiate, or it can ignore it. It can do whatever it wants, but in this case, it initiates a graceful shutdown. And then when the kernel checks again, there's no pending signal, so nothing more happens. And then you have what happens in Kubernetes, or in Docker, or other containers, where the signal is sent. It's not picked up by any handler. It's pending, but the kernel's like, okay, there's nothing more I can do, or will do, actually. Oh, okay. It's demo time. So here I have 5 different scenarios. Here I have a Python file, which basically just calls sleep as a subprocess. The Docker file, which runs it. I'm gonna build this. And run it. And then Docker PS. It's 007A, Docker exec, bash. Oops. Here we see that we have the Python script as PID1, and we have the sleep as PID7. And you can see now that if I try to kill PID1, nothing happens. If I try to kill PID7, that's not a protected process. And we exit. Not because the PID1 was terminated, but just because it finished, because the subprocess it ran completed or was terminated. Then we have go, which is similar, but now we do the sleep inside the application. And here we see we copy it and execute it. And run it. Docker PS. Go test is 07A, Docker exec, bash. Oh, serious crap. 0 Yeah, ps-ef. Here we have the mygo application running as PID1. What do you think will happen if I try to kill this one? Will it exit? It will. Why is that? That's because Go adds signal handlers to their applications. Oops, let's see here. Let's go out. Here we have, okay, script. Here we have two scripts. We have a handler script, which has a trap for the sig term and exits if it finds it, but also printing caught sig term, so we know that it actually caught it. And then we have the entry point, which is just calls the handler. And the Docker copies both and executes the entry point. So Docker build script. I'll just do this. SCT. Docker run SCT. Docker PS. FF1B. Sorry. Bash. Docker. PS-ef. So here we have two scripts running, and the sleep one that's executed by the handler script. If we kill one, nothing is happening again, because we know that, well, it was Python last time, but Bash doesn't have any handlers by default either. So then we kill 7, and everything exits after the 1 second sleep. Again, because the handler script, as you can see up here, caught the sig term, exits, and the entry point just finishes. So then we go to the init. This is pretty cool. Because one thing you can do to circumvent this behavior of, or to sort of navigate or tackle this behavior of PID1 being the only recipient of the sig term, is that you can use an init application to get that PID. And the init application, sorry, I'm getting ahead of myself. Here we have the same handler script, and the Docker file is, yeah, is similar, but now we download this application called dump init, and that is set as the entry point, where the handler script is set as arguments to that. So then this makes it so that dump init has PID1, and this init program propagates signals to its children. So if we do docker build, init test, 95 DD. Here we see init has PID1 and the handler script has PID7. And then what happens if we try to kill PID1? It exits and we write this called sig term, which is coming from the script. So here we can see that the sig term has been propagated to its children. Okay, just gonna have a drink. Last demo is Kubernetes. Here we have a setter script I'm just going to run to ensure that we have what we need. Set up a cluster, build a Go app, build a Python app, and load them into the cluster. And then I have this, these are the two pods. They are identical, except that they're using test Go and test Py. It's the only difference. And then we have, just going to do this. So now we create both of them. They are running, and then we delete them. So you remember how they behaved, how they tackled signals. And this is what the effect is in Kubernetes. Go is gone, but pi is not gone. So what happens here is that the sig term has been sent to the container, but there's no handler for it. And since it's PID1, the kernel doesn't do anything. So what we're trapped in is this grace period. So now this is going to stick around for 30 seconds until it's killed by sig kill. I should talk a bit slower so we don't have to wait that much. There we go. Okay, so we're back. Okay, all of you who just zoned out, you can come back now. Now we're back into Kubernetes world. And this is something that's pretty important to know when you're working with deployments. This is the life cycle of containers in a pod, during creation and during termination. So on the left side here, you can see that we have a pod with 2 init containers and 2 main containers. And during the creation of this pod, the top of the init containers will be started first. And when this is ready, it will move down one by one through the init containers. And then when the last of the init containers have finished, it will start all of the... Sorry, I forgot these questions. I knew I would. Let's see if there was actually questions. No, wasn't. When all of the init containers are started, the main containers are started all at once. And then at the other end of the diagram, when we terminate the pod, we first start by setting sig term and eventually possibly sig kill to the main containers. And when all of the main containers have exited, we kill off, or we start by terminating the sidecars, and then we move from the bottom up. So in that way, we can actually have sidecars depend on each other. And this feature, or this functionality with sidecars, is pretty new. We've had sidecars in Kubernetes for a while, but they've been implemented just as main containers running alongside the other, and it's been a bit finicky to make them work properly with being available before the main container and being available until the main container, like main container, has finished. But with this functionality here, we specify sidecars by having them alongside other init containers, but specifying restart policy always. So that is the only difference. Oh, even further back up. The problem was that we had a race condition, right? We had a race condition between the kubelet doing this termination and all of the network thingies, routing, updating, and all of that. So what can we do to alleviate this or to sort of mitigate it? We have 3 options, is what I found. I'm not gonna go through how I found all of them because this is only an hour and it's boring. But the 3 of them are: first, drain state, which is something or a state where you catch the sig term coming from the kubelet or from the container runtime, and then you lie to Kubernetes, basically. You say, okay, yeah, I'm going to shut down, and then you don't. You respond normally to traffic, and you succeed the liveness checks, but you fail the readiness check. So what this does is that it removes the pod from the endpoints before it can actually stop receiving traffic. So this looks a bit like this in the diagram, where it postpones the graceful shutdown and postpones the ending of serving new requests until the IP tables or the routing has been updated. Another thing you can do is to, well, no, this is how it would look, sort of like, I'd say pseudocode. This is actually Python Flask API. Here you have a signal catching, catch sig term, and execute start drain. Start drain sets the global variable of draining to true and executes the task shutdown asynchronously. And then this again sleeps for 10 seconds before exiting. And then we have the 3 endpoints down here. The live one will always respond okay. Ready will respond with a failure if we're draining. If not, it will respond okay. And then business will respond as usual. So ignoring the fact that I'm using global variables and just system exit and not actually doing a graceful shutdown here, this is like the principle of it, at least. Then the second option is blue-green deployment. And this is not as much of an option as it is just telling you that if you already have some tooling for this, for example, using a service mesh, etc., then you won't have this problem, this race condition, because you set up the service and deployments of each version before you do any kind of traffic rerouting. So all of the endpoint slices, etc., they're already there. But the drawback of this is that this won't help you if your pod's been rescheduled. So if you do a node upgrade or like a cluster upgrade, then you will still be vulnerable to the 502s. And then lastly, we have the pre-stop hook, which can be used to sleep. And recently, we also actually got the explicit action to sleep. And yeah, can you guess sort of what's the, well, sort of, again, getting ahead of myself. This is how it would look in the diagram, and we execute or we postpone the whole SIG term sending. So the application doesn't know what's happening, and that's a big pro, or like that is a drawback of the drain state. You're dragging Kubernetes specific functionality into your application, something that really shouldn't belong there. So this is a benefit, that the application doesn't know or doesn't care what's happening outside. This is a Kubernetes specific thing. It should stay outside of the applications. So can you guess who the winner is? It's the pre-stop hook. And when I discovered that, I couldn't really believe it because it seems so arbitrary. Is it sort of like the recommended and documented solution to just sleep for some seconds? And I guess the reason for this is that there is a distinct separation of concerns between what handles your container running, like the kubeless responsibility, and the container runtime's responsibility, and what handles the traffic and or the routing, the network. And you don't want to convolute that with something that isn't really that big of a problem and can be mitigated by other ways. So I respect this decision of keeping that elegance in the design and just sticking to the very simple principles. So there you have it. This is how you achieve absolutely zero downtime deployment in Kubernetes. You use a pre-stop hook. That's all I had. It always takes a bit shorter than you think, right? If you have any questions, we have time for that now. Either I think I can see your hands if you have them, or you can send me on Slack. If not, I'll be around a little bit, and enjoy the rest of the conference.